Hello, welcome to a really quick section, 4.5 on linearization, which you have already done, that is tangent lines, and differentials, which we haven't done. What we're going to do is linear approximations and tinker with some differentials. Okay, linearization, again, all linearization is a tangent line. So to introduce some new notation, delta x is the real change in x as we move along the curve. Delta y is the real change in the function's y value as we move along. Dx and delta x are always going to be the same because in our simulation or our model or our approximation, we're going to make this step every 1 second, every infinitesimal, whatever. So dx and delta x are the same. Dy is the y value that we would have gotten if we'd done the tangent line. Dy and delta y probably will not be the same. But if the dx or the delta x is small enough, the dy will be really close to the delta y, which is why we use calculus. Okay, finding the linearization. To find the linearization, that is just finding the derivative and using that to get the slope, plug it in, create the tangent line. Okay, so we need a point and a slope. Plugging the point in, plugging in 0 for x, y equals natural log of 1. Natural log of 1 is 0, so the coordinate we're going through for our tangent line is 0, 0. To find the derivative or to find the slope, change in y over change in x. That is the derivative of natural log of this, which is 1 over this times the derivative of 1 plus x, which is just that. Then the slope at x equals 0 is just 1. So the linearization is, and just to be irritating, they have started to, instead of saying y, they're now going to say L of x for linearization of x. Okay, fine. L of x minus the y value equals slope times x minus the x value. So our linearization is just x. So if we want to find what is the linearization, what's the approximation at x equals 0.2, I don't know what natural log of 1.2 is. However, in calculus, it's telling us it's really close to just whatever x is. So if x was 0.2, the approximation is 0.2. Now, is it an over or under approximation? We are going to use the second derivative because that's what they told us to do. Taking the second derivative, multiply by the power, which is -1, lower the power, which is -2. No matter what x value I plug in, the second derivative is always negative, so it's concave down. My linearization is a tangent line. That tangent line is always going to be above, so my approximation is going to be an overestimate. And checking on the calculator, natural log of 1.2 is 0.182. So the real value is a little bit smaller than our approximation, and that's what we had said in our conclusion. Okay, differentials. Differentials, for the purposes of what we need to do, is just treating dy dx as a fraction. So algebraically, as y is changing, how is x changing? We can cross multiply and say the change in y is the derivative of x times dx. So this is a manufacturing kind of application. If we are making something and change the length of the accuracy of the length of manufacturing this side, how is that going to change some other side? And then graphically, again, it's the dx and dy and delta y. And that, here's one example. If f of x is x squared, we want to find dy and delta y when x is 1 and dx is 0.01. And we don't do much with this in this class because it generally needs a calculator and has you type things in to find the real y value and then the approximated y value. But, all right. Right here, dy dx, cross multiply, dy is 2x dx. When x is 1 and dx is 0.1, the change in y would be 0.02. What is the real change in y? F of 1 is 1. F of 1.01 is 1.01 squared, which is 1.0201. dy, the delta y, change in y, is my ending function value minus my beginning function value, because that is the change in y. y2 minus y1, the ending y value minus the beginning y value. Here's delta y. Here's dy. Which is larger in y? Well, looking clearly, delta y is larger, but as we just did in the previous example, do the second derivative. This was the first derivative. The derivative of that is 2. No x's, just 2. That is a positive concavity. The tangent line will be underneath. So this is an under approximation of that.